All right, everybody. On to the next segment in our discussion. We're talking about, I don't want to call it Faraday's Law because we'll be talking about Maxwell in a bit as well. So part of it is Faraday's Law. And what that is about is, let's say that you have, let's say, conducting loop. We'll begin with it this way, right? Conducting loop. The loop is sitting like that, like this, and you were to drive a magnet into the loop, right? So all you do is basically drive a magnet in and out of the loop, right? The changing magnetic flux in the loop will create a current in the loop. Right? So by Faraday, so you could do it this way, or you could have something else producing a magnetic field that goes in the loop that changes in time, and you can change the flux in time by changing the strength of the field, by changing the area or the angle. So basically, if you have now a loop like this, and you got a magnetic field, right? And the magnetic field goes into the loop, or goes through the loop, and the loop area is A, right? We're going to begin with this slowly. So this is B, and B is a function of time somehow, right? Then the changing magnetic flux in the loop will produce a current in the loop. More importantly, it'll produce why there is current in the loop, right? And you can see that with, you can. I have a demo that I'll put up for you. It's got other stuff in it. It's got waves. It's got a bunch of things in it too. But hopefully you'll see that as well. You got a coil and hooked up to a galvanometer, and you drive a magnet in and out of the coil, and you can see, the current changing direction and changing value, depending on the rate of change of flux in the loop. So two parts to this. One is Faraday's Law, which says that the induced EMF, epsilon induced, is equal to d phi magnetic by dt. Okay, what is phi magnetic? Phi magnetic is the flux. So phi magnetic is B times A if everything is nice and uniform, and phi magnetic proper formula, proper expression for it is the double integral over the surface of B dot dA. So what you have now is that epsilon induced. Epsilon is electromotive force. Okay, and distinguish this from epsilon. This epsilon is not the same as this epsilon. Two of them. What is electromotive force? Electromotive force, what you've seen before, is to say, battery is, source of electromotive force. So you have some sort of resistor here, and electromotive force. Battery is a source of EMF, right? Chemical cell, or what have you. That is nothing but an electron pump. It will, you have a resistor here, you have electrons, they're going to go this way. What it does is it creates a current in the circuit. So an EMF is a sort of an electron pump, like having a battery, right? The only thing here is that, when you have a time varying magnetic flux in a loop, right? That's going to cause an EMF in the loop, right? It's sort of like having the battery spread over the loop, right? Not exactly, because the nature of the fields is different. We'll be getting that later. But effectively, when you change the magnetic flux in the loop, right? By Faraday, or what we see is just the fact that you have either a bar magnet or a magnetic field changing with time, or you change the area or change the angle, between the field and the area, you're going to end up with an induced EMF. Okay? And what that does is it's going to drive the charges, drive the electrons in a certain direction, and cause the current to flow in the opposite direction, the conventional current. So, I mean, the EMF is going to push electrons this way, and we talk about conventional current, we don't talk about electron flow, we talk about the flow of positive charge carriers, so you're going to have a current going in this direction, that's from a battery, and the same thing will happen here. Now we need to look at the direction in which your current will flow, and that's where Lenzs Law comes in. Lenzs Law states that the direction in which the current will flow in the loop, and the current is flowing because there is an electric field, right? Because there is an EMF in the loop, induced EMF. The direction in which induced current will flow is such that it opposes the change in the flux. So, if, for example, let's take a look at this. If the magnetic field is increasing in the forward direction, this way, down, so the value of the magnetic field is going up, right? Which direction would the current be induced in? Pause for a second and think about that. You need to keep in mind that that induced current will act to oppose the change in the flux. So, I'm hoping you did that. The magnetic field is increasing in magnitude and pointing this way. It's getting stronger in this direction. The induced current wants to act in such a way as to oppose this change. So the right-hand rule, right? Which direction must the current flow in the loop so that I have a magnetic field opposing the change in the flux? The flux is increasing in the forward direction downwards. To oppose that, I need an induced magnetic field that's going to point up. And by the right-hand rule, if I line up my hand with the loop this way, I'm going to end up with an induced current this way, I induced, that will create a magnetic field, B induced, that will oppose the change in the flux. And vice versa, if the magnetic field strength was decreasing, the current will flow in the opposite direction. So to complete the picture, epsilon induced with Lenzs Law, this becomes part of Maxwell's equations. We have a minus sign to indicate that the change in the flux is resisted by the induced EMF or the induced current, okay? Because the EMF will cause an induced field, as we'll see shortly, and the induced field will point in the same direction as the induced current. That will act in such a way as to oppose the change in the flux. That's what the minus sign there does. Okay? Now, for a more formal formulation of the law, okay, we say that epsilon induced is equal to minus d by dt of the double integral of b dot ds over the surface. This is my surface here, right? All right. So the fact that there is an epsilon induced, right, indicates that, epsilon is what? What is epsilon? Epsilon is the electromagnetic force. It's like a potential difference. It's a potential difference across the circuit, okay? When you have a battery, it's easy to visualize. You have potential difference between the terminals of the battery, and that's the same as a potential difference established across the circuit here, right? When you have an induced EMF, it's not localized. It's not like you have a battery set up somewhere here. It's like having the battery spread all over the slope. But still, the reason you have a current flowing here is because you have an electric field here, right? And that electric field is what pushes the electrons down, pushes the positive charge carriers up, if you want, and creates a current. So there is no current without an electric field. And here we have a current flowing this way, therefore we must also have an electric field, E induced, pointing this way, right? We'll talk about that in a little bit more detail But for now, we'd like to do some examples of, where we calculate the epsilon induced with, play different games, different geometries, and, different setups to get the idea across. But keep in mind this important relationship between I induced and the E induced that causes it. This is the most important part of induction in this case. It's not the I induced. I induced is important, but the reason there is an I induced is because there's an E induced, and the EMF is related to the E induced. Right? Let's think about this for a second. Right? If I were to look at the potential difference between 2 points here, right? Between 2 points here, let's say point A and point B, right? We say that the potential difference between them is E times the distance. So what's an expression for the EMF induced around the circle? It's kind of like, it is really interesting in that, for the first time, you have potential difference between, you go this way, you have E flowing that way, so this point is a different potential than this point, and we keep going this way. E times L, or E times dL, integral of E dot dL basically will give you the potential difference going forward until we get back to here. And we can see now that because E is this way, and what is the expression for the potential difference between 2 points? Well, delta V is equal to negative the integral of E dot dL. And this delta V is of the same nature as epsilon induced, right? When you sum the delta V's all across the loop, you get the epsilon induced all over the loop. Right? It's very, very significant here in that for the first time, we have this epsilon induced being the integral of E dot dL around a closed loop is not equal to 0. The integral of E dot dL around the closed loop is equal to minus d by dt, double integral over the surface of B dot ds. Okay, so Faraday's law begins like this: epsilon induced is equal to d phi by dt. The direction comes from Lenzs law, and how you invoke the direction in there in this dot product equation is, you could just think of it intuitively in that you want the induced current to oppose the change in the flux, but you can also use the right-hand rule in the same way that we discussed in the Ampere's law limitations and clarifications. The same thing, same holds in that case as well, and that can be handy for you. Okay, so the only thing we're introducing now that is a bit of a leap, and we've seen that before, is we're making the connection between this epsilon induced. Epsilon induced is potential difference. How do you get potential difference? You can think of it this way. It's the integral of E dot dL from here to there. That gives you the potential difference across the circuit. And because this battery is more or less kind of scattered all over that, if you want to think of it this way, all over that, we have an electric field that is going to point in circles here. Yeah, that's what's driving the current to flow. And the interesting part is that we have an integral of E dot dL around the closed loop that is not equal to 0. Right? Why is that significant? Right? If you have an object and you move it in a closed circle like that, what is the change in potential? It's 0. Integral of E dot dL is change in potential. If you're sitting in front of a point charge and you move around the closed loop, the change in potential or potential energy is 0. The integral of E dot dL around the closed loop is always 0. In this case, it's not. What we've seen so far is that for electrostatic fields, if you have a point charge or a plane sitting in front of a plane, what's the change in potential in front of a plane? I go E times L this way, nothing that way, minus EL that way, and up that way 0. This and that cancel out, no change in potential here. So imagine you have an infinite plane here. There is no change in potential as I go this way and that way. Right? I have to move with the field. If I move with the field, I drop in potential. If I move against the field, I rise in potential. And if I go around the loop, the change in potential is 0. Yet now we have this kind of electric field whereby if you go around a circle, right, it gives you the change in potential all around the circle. You can think of it this way. right? It's kind of funny because you go around the circle, and what typically you've expected to, if you go around the loop in the presence of electric field, to have zero potential change, zero change in potential. Now with this induced electric field, we have a different game in that we have Faraday's law, which says that there is a induced EMF which we can measure, and that induced EMF is caused by an electric field which causes a current to flow, right? Opposes the change in the flux, but this field multiplied by dl integrated over the loop will give me the overall epsilon induced, right? So you can do it intuitively, or you can do it with, with our understanding of the, relation between the area vector and the direction of integration around the loop that we introduced in the last part of Ampere's law. Either way, it's fine. Keep this in mind, because there is a fascinating part that Maxwell introduced later, right, that we'll talk about in a bit. Okay? For now, we have Faraday's law in this form with Lenz's contribution, and we have Faraday's law in this form. We're going to this is the integral form of of this law, right? Look up the differential form of the law. It involves nebulas, so please take a look at that if you want. It's in the notes as well. We're going to be covering only the integral form of some of Maxwell's equations. Okay. So now what I'd like to do is play some games and see how we can develop more of a intuitive, qualitative, and quantitative understanding of Faraday's law, right? So please keep in mind that I've introduced a lot of stuff in the last few minutes, right? Usually we just say epsilon induced equals to d phi by dt, and we go play games with that with the minus sign. What we have introduced today is that this epsilon induced across the loop is really nothing but the integral of E dot dl, right, across the loop. And so this was something that we threw in today, and we will be visiting that shortly. Right? For now, though, right, we will do some examples involving Faraday's law. Okay, lights went out, and we're back. Right? Okay. So how do we? Okay, let's say that we are sitting in a region where the magnetic field points this way. Right? And you have the following setup. You've got a wire. Okay? Got a wire, and you got a conductor. Okay, so this is a conducting wire. And you've got a conducting bar, and the bar sits in contact with the wire. Let me make it a little bit bigger, this loopy part here. Right? Let's say that this thing sits here, and what you're going to do now is this bar is in contact here and there, right? So think about what's going on here. It could be a bit confusing, but shouldn't be that bad. This is one of the simplest ways to introduce what happens with Faraday's law. So you have a uniform magnetic field, okay, pointing into the board here, everywhere, right? And what you're going to do now is in this B, and this is B, we'll call it B external, okay, external magnetic field. This magnetic field is uniform and constant. What you're going to do here is you're going to pull this bar, this conducting bar, you're going to pull it this way at speed v. Okay? All right? And let's say that at this given moment, the resistance of this part including the wire, is now R. And that will change because the wire will get longer. So look at what's happening here. And this is open on this side, okay? And it doesn't have to be open. It could be interesting when we close it, but for now, this part of the wire is open, right? The only loop, we have to have a loop over which there is a magnetic flux, and the only loop there is here, okay? There is no loop here, nothing for the current to flow in. And what's happening over here? Let's say that the loop has length L and width X, and this is moving at speed V. Okay, so what's happening here? You've got a magnetic field B that is uniform. The field is not changing, but the flux in this loop is changing. Why? Because the area is getting bigger. There's going to be an induced magnetic, an induced current, induced magnetic field, induced current, induced EMF. First question is, in which direction will the current flow? Well, what's happening here is that the field points, the external field, B external, points in. As the bar moves out that way, the area is getting bigger. And flux is B times A, because B is uniform. Don't even have to integrate here. A is getting bigger. The flux is increasing in the forward direction, right? What that means is now we have to have an induced current that opposes the change. Pause for a second and think about which way the current will flow. To do that, you can do that using the the right-hand rule, or conceptually invoking Lenzs Law, that minus sign, to indicate that the induced magnetic field will oppose the main magnetic field, and which direction must the induced current flow in to do so. So we have a magnetic flux that is increasing in the forward direction, and we want to oppose that. The way to oppose that is that we have to have an induced magnetic field that is going to point in this direction. That is into the board, this is out of the board. So the induced magnetic field is these red dots here, okay? That is B induced. And for that to happen, following the right-hand rule, means that I induced that creates this field, I induced must be in this direction, okay? So in here, we don't care, not much is gonna happen out there. I induced is this way. So that is I. What is the value of this I induced? We'd like to know what the value of the current is. Well, we have, epsilon induced, okay, is equal to d phi magnetic by dt. Okay, I'm going to take absolute values here, okay, because we'll invoke the direction later if we want to figure it out already. So epsilon induced is equal to, now what is d phi by dt? D phi by dt, what is phi? Phi is B times A in this case, and A is L times X, so phi is d by dt, okay, of B L X, right? And that's equal to B is constant, L is constant, d by dt of X is V, so it's equal to B L V, okay? So epsilon induced is B L V. And if the resistance of the loop is R, then epsilon induced is I induced times the resistance of the loop at this time is equal to B L V, and I induced in the loop, you can measure it to be equal to B L V over R, okay? We're going to continue playing games with this example. I'd like to look now at, what's going on here? You got some interesting stuff going on. We have, somebody pushing this at a constant speed V, but there is magnetic resistance. What does that mean? You got a magnetic field that is being induced to oppose the main magnetic field, okay? It's going to take force to pull this bar at a constant speed. So what do you have now? You've got a magnetic field that induces a current and will interact with the current as well so as to create magnetic resistance, and we'll talk about that shortly. Before we get to that part though, I have to talk about magnetic forces, which we'll be following in the next part.